So in this video, I'm just going to go back over the initial video we did in part 2, where we looked at the maximum range, and I'm going to actually use it again just to derive the time of flight, which we did look at in part 2. But I just thought if we go over it again and look at that derivation in more detail, it might just give you a little bit of a deeper understanding. So we have the same parabola as we had last time, a projectile being projected at an initial speed of u at an angle of theta to the horizontal. I've already got my components, so I've got my two vectors there of velocity of u cos theta in the horizontal, u sin theta in the vertical as before, and I've also set out the horizontal range equation, and I've looked at my vertical directions as well, which is what I'm going to be looking at in this video. And I formed that Suvat equation. And remember, just to clarify, because I took upwards as positive, my initial velocity was u sin theta, and my final was minus u sin theta, because remember, with no air resistance, speed of projection is equal to speed of return. Acceleration is minus g, because obviously upwards is positive and gravity acts to the centre of the Earth downwards. And t is my time of flight. So I'm just going to go through that little bit of derivation again. So remember, we had a Suvat, and I recognised that I would need to use v equals u plus at as my Suvat equation, and I immediately rearranged it for t, which is the time of flight, equal to v minus u over a. Substituting in, I get minus u sin theta over g is equal to my time of flight. Simplifying, I get minus 2u sin theta over minus g, and the minuses cancel, giving me a time of flight equal to 2u sin theta over g, and that is our general equation for the time of flight of a projectile.